Hello everyone, am I audible?
Yes, sir.
Okay. Okay, let's start. Today, first we will solve a problem. Hello everyone. In this video, I shall discuss the solution of question number 33 of GATE Physics 2017. This is a multiple choice question. Consider n non-interacting distinguishable particles in a two-level system at temperature T. The energies of the levels are 0 and epsilon, where epsilon is greater than 0. We need to find out the population of particles in the level with energy epsilon in the high temperature limit, which means when kBT is much larger than epsilon. Let's solve this question. So in this question, there are two energy levels with energy 0 and epsilon. So the single particle canonical partition function Z1 is equal to e to the power 0 plus e to the power minus epsilon by kBT. So Z1 is equal to 1 plus e to the power minus epsilon by kBT. Now the probability of finding a particle in the level with energy epsilon is equal to e to the power minus epsilon by kBT by Z1. Here Z1 is equal to 1 plus e to the power minus epsilon by kBT. So in epsilon by n is equal to e to the power minus epsilon by kBT by 1 plus e to the power minus epsilon by kBT, where in epsilon is the population of particles in the level with energy epsilon and n is the total number of particles. So the population of particles in the level with energy epsilon is equal to n e to the power minus epsilon by kBT by 1 plus e to the power minus epsilon by kBT. In the limit kBT much greater than epsilon, we have epsilon by kBT much smaller than 1. In this limit, we approximate e to the power minus epsilon by kBT as 1 minus epsilon by kBT. As epsilon by kBT is much smaller than 1, we can also approximate it by 1. So we replace e to the power minus epsilon by kBT by 1 in this expression. Then we get in epsilon is equal to n into 1 by 1 plus 1. So in epsilon is found to be n by 2 in the high temperature limit. So correct answer is n by 2. So option A is correct.
Hello. Is there any question? Hello, am I audible?
Yes, sir.
So it is clear, right? There is no question, I think. If there is no question, then let's solve another problem.
Is given by minus del beta log choice. Hello everyone. In this video, I shall discuss the solution of question number 5 of GATE Physics 2019. This is a multiple choice question. Consider A one-dimensional gas of n non-interacting particles of mass m with the Hamiltonian for a single particle given by h equal to p square by 2m plus half m omega square into x square plus 2x. We need to find out the high temperature specific heat in the units of R equal to n kb, where kb is the Boltzmann constant. Let's solve this question. In this question, the Hamiltonian h equal to p square by 2m plus half m omega square into x square plus 2x. This can also be written as p square by 2m plus half m omega square into x plus 1 whole square minus half m omega square. So this is the single particle Hamiltonian. The single particle canonical partition function is given by integral dp integral dx by h into e to the power minus beta h. Here we replace h by p square by 2m plus half m omega square into x plus 1 whole square by 2 minus half m omega square. So the single particle canonical partition function z1 can be written as e to the power beta m omega square by 2 by h into integral dp e to the power minus beta p square by 2m into integral dx e to the power minus beta m omega square by 2 into x plus 1 whole square. Now we'll evaluate these two integrals. To evaluate these two integrals, we consider that beta p square by 2m equal to u square and beta m omega square by 2 into x plus 1 whole square is equal to v square. Then we get z1 equal to e to the power beta m omega square by 2 by h into integral du e to the power minus u square into 2m by beta whole to the power half into 2 by beta m omega square whole to the power half into integral dv e to the power minus v square. Now the integral du e to the power minus u square is equal to root pi. So we replace these two integrals by root pi. Then we get the single particle canonical partition function z1 equal to e to the power beta m omega square by 2 by h into 2m pi by beta whole to the power half into 2 pi by m beta omega square whole to the power half. After some simplification, it can also be written as z1 equal to e to the power beta m omega square by 2 by h into 2 pi by beta omega. Here h equal to 2 pi h cross. So we get z1 equal to e to the power beta m omega square by 2 by h cross beta omega. So the n particle canonical partition function Zn is equal to Z1 to the power n, where Z1 is the single particle canonical partition function. Now the average energy is given by minus del beta log Zn. Now this Zn is equal to Z1 to the power n. Using that, we get the average value of energy is equal to minus n del beta log z1. Using this equation, we get that log z1 is equal to beta m omega square by 2 minus log h cross beta omega. After taking differentiation with respect to beta of this quantity, we get the average value of energy is equal to minus n into m omega square by 2 minus h cross omega by h cross beta omega. After some simplification, this can be written as minus n into m omega square by 2 minus kBt. Here we have used that beta equal to 1 by kBt. Now we have to calculate the specific heat. So to do that, we have to differentiate the average energy with respect to temperature. Here the first term is independent of temperature, so the differentiation of the first term is 0, and from the second term, if we differentiate it with respect to the temperature, then we'll get n kb. So Cv equal to n kb. So the specific heat in the unit of n kb is 1. So option A is correct.
Hello, any question?
No, sir.
So it's completely clear, right?
So what is the meaning for high temperature specific heat?
Okay. So the Hamiltonian was this. So if you consider the Hamiltonian to be classical, then it's already the high temperature specific heat. But if you calculate the specific heat, but if you consider this Hamiltonian to be quantum, I mean this is operator, this is also, these are operators. Okay, in quantum mechanics these are not just variables, these are operators. X and p do not commute. In that case, if you calculate the specific heat and if you go to this t tends to infinity limit or beta equal to 1 by kBt, so beta tends to 0 limit, then you are actually getting the same thing, I mean the specific heat obtained for classical Hamiltonian. Okay, so in this question the high temperature specific heat means that the particle is classical. Okay, clear?
Okay, yes, sir.
Okay, any other question?
Sir, these videos are quite fast, so it is hard to write also with the question or problem.
Okay,
If it
so
could be a little slow, then
mm,
it would be great.
the videos will be available in the portal, right?
There is
The
only a link provided of recorded videos.
you can see them and pause them whenever you require, right? If you
So because I also have the same issue. I feel it is a little fast so that we couldn't process before the video is complete actually.
okay, so one thing I can do, I can sharing my screen and I can explain it again. I think it will be better.
Yes, sir.
Okay, So this was the question, right?
Yes, sir.
Okay. So the Hamiltonian was p square by 2m plus this half m omega square into x square plus 2x. So this x square plus 2x can be written as x plus 1 whole square minus 1, right? Yes or no?
Yes, sir.
Okay. And you all know about this canonical partition function. I have discussed it before. I mean, not the last class. I think in our second class. Okay. So this is the canonical partition function. This is just a definition. So there is integral dp integral dx by h. H is the Planck's constant into e to the power minus beta h, and h is this Hamiltonian. Okay, and beta is 1 by kBt, inverse temperature. Okay, now I put this Hamiltonian here, just replacing it. Okay, so this term is independent of x and p, so I will keep this out of this integral. So e to the power beta m omega square by 2 is outside this integral, and inside the integral we have dp e to the power minus beta p square by 2m into integral dx e to the power minus beta m omega square by 2 into x plus 1 whole square. Okay, now we have to evaluate these two integrals. For evaluating the first integral, we'll assume that beta p square by 2m equal to some, say, u square. Okay, so this means p equal to root over 2m by beta into u, and similarly we will assume that beta m omega square by 2 into x plus 1 whole square equal to v. Okay, clear?
Yes, sir.
Okay, so just I have replaced here, okay, these two things, then we get this equation. Okay, z1 equal to this thing. Okay, now this integral du e to the power minus u square, where the limits of the integral are minus infinity and plus infinity, is equal to root pi. So this integral is equal to root pi, so we get this thing from the first integral, and from the second integral we get again root pi. Okay, and after doing some simplification we get this z1 equal to this, and what is h? H is the Planck's constant, which is equal to 2 pi h cross, and if you take h equal to 2 pi h cross, then 2 pi and 2 pi cancel out, and your z1 is equal to this thing. Okay, clear?
Yes, sir.
Okay. And this in particle partition function is equal to single particle partition function to the power the number of particles. Okay, this we can show also. Okay, first understand this problem, then if we have time then I'll show it. And this average energy can also be written as minus del del beta of log zn. Okay, so this zn is equal to z1 to the power n, so you can write it as minus, sorry, you replace here zn equal to z1 to the power n, and log of z1 to the power n is equal to n log z1. So we get average energy equal to minus n del del beta of log z1. Now z1 is equal to this thing. If you take log on both sides, then you will get log z1 equal to beta m omega square by 2 minus log h cross beta omega. Okay, clear?
Yes, sir.
Now if you differentiate it with respect to beta, then you will get from the first term m omega square by 2, and from the second term you get 1 by h cross beta omega in the denominator, and in the numerator you have h cross omega, and h cross omega and h cross omega in the numerator and the denominator cancel out, and you have 1 by beta in the second term. And now we know that 1 by beta is equal to kBt, so the average energy is equal to this thing. Now the specific heat at constant volume is equal to del del T of average energy at constant volume. So here the first term of this average energy is independent of temperature, so the differentiation of this thing with respect to temperature is 0, and from the second term if you differentiate it with respect to temperature, then you will get n kb. So we are getting n kb, and in this question we have to write down the answer in terms of n kb. So I mean Cv equal to say x into n kb. We need to find out the value of x, so the value of x is 1. Okay, any question?
Sir.
I can also share the PDF with you if you want for this problem. Just let me see whether I can do it. Okay. In the first problem, do you want to see the PDF version? Anyone?
Yes, sir.
For the first problem?
Yeah.
Okay. This was the first problem, right? Today?
Yes, sir.
Okay. So there are n non-interacting distinguishable particles in two-level system at temperature T, and these two levels have energy 0 and epsilon. And what is single particle canonical partition function here? Just give me 1 minute. What happened? The single particle canonical partition function is equal to this thing. Okay, sum over I u to the power minus beta ei. Okay, and here ei can be equal to 0 and epsilon. So put the values here, you will get z1 equal to e to the power 0 plus e to the power minus epsilon by kbt, and beta is equal to 1 by kbt. Okay, and what is the probability of finding the particle in the level with energy epsilon? This is equal to e to the power minus epsilon by kbt by z1. This I have discussed in previous class when we are discussing about canonical distribution. Okay, now let's say there are n particles, okay, and n epsilon number of particles are in the level with energy epsilon. Then what is the probability of finding the particle with energy epsilon? This is equal to n epsilon by n. This is clear, right? Hello?
Sir.
Okay, so this is equal to this thing for any canonical distribution. This is the probability, and this is the normal definition of probability. This n epsilon by n is the general definition we usually use for defining probability, right? And this is the probability for canonical distribution. So these two are equal here. So n epsilon is equal to this n into e to the power minus epsilon by kbt by 1 plus e to the power minus epsilon by kbt, as here z1 is equal to this 1 plus e to the power minus epsilon by kbt. Okay, now you have to find it in the high temperature limit. This high temperature limit means it is given here that kbt is much greater than epsilon. This kbt has the dimension of energy, right? And the epsilon has also the dimension of energy. So this temperature, the energy scale corresponding to temperature, I mean kbt, is much greater than epsilon in the high temperature limit. So in this limit we have also epsilon by kbt much smaller than 1. Now you all know about Taylor series expansion. This e to the power x is equal to 1 plus x square by 2 plus higher order terms, and in the limit x much smaller than 1 will neglect the higher order terms, and we restrict ourselves to this 1 plus x. There is some noise, please mute yourself. So e to the power minus epsilon by kbt can be approximated as 1 minus epsilon by kbt, and if you go to extreme high temperature limit, when T tends to infinity or epsilon by kbt much smaller than 1, in that limit you can also approximate it by 1. You can also neglect the this second term, I mean epsilon by kbt term. Okay, so if you do that, then e to the power minus epsilon by kbt is approximated by 1, then you get n in the numerator and in the denominator you get 1 plus 1. Okay, so this is equal to n by 2. Okay, any question here? Hello?
No, sir.
Okay. Now let's solve another problem.
Hello everyone. In this video, I shall discuss the solution of question number 46 of GATE Physics 2016. This is a multiple choice question. A two-level system has energies 0 and E. The level with zero energy is non-degenerate, while the level with energy E is triply degenerate. We need to find out the mean energy of a classical particle in the system at a temperature T. Let's solve this question. In this question, there are two energy levels with energies 0 and E. The level with energy 0 is non-degenerate and the level with energy E is triply degenerate. So the single particle canonical partition function is given by sum over I e to the power minus EI by kBt. So the single particle canonical partition function in this problem is equal to e to the power 0 plus e to the power minus E by kBt plus e to the power minus E by kBt plus e to the power minus E by kBt. Here e to the power minus E by kBt appears 3 times because the degeneracy of the energy level with energy E is 3. So Z1 is equal to 1 plus 3 e to the power minus E by kBt. Now the mean energy is given by sum over I EI e to the power minus EI by kBt by Z1. So this will be equal to 0 plus e to the power minus E by kBt plus E into e to the power minus E by kBt plus E into e to the power minus E by kBt, and Z1 is equal to 1 plus 3 into e to the power minus E by kBt. In the numerator, E into e to the power minus E by kBt appears 3 times because the degeneracy of the level with energy E is 3. After some simplification, the mean energy turns out to be 3 E to the power minus E by kBt by 1 plus 3 e to the power minus E by kBt. So this is the mean energy. So in this question, option D is correct.
Now I am sharing the PDF of this question. So in this question, the system has
It's
two
clear there
levels.
is no need to.
Okay. So the main thing in this question was there are 3 levels with energy E, which means the level with energy E is triply degenerate, or the degeneracy is 3. So Z1 is equal to this thing. Okay, this e to the power minus E by kBT appears 3 times. Okay, similarly here also, that's all, nothing else. Okay. Okay, any other question?
No, sir.
Okay, so let's solve another problem.
Hello everyone. In this video, I shall discuss the solution of question number 53 of GATE Physics 2018. This is a numerical answer type question. The partition function of an ensemble at a temperature T is Z equal to 2 cos hyperbolic epsilon by kBT whole to the power n, where kB is the Boltzmann constant. The heat capacity of this ensemble at T equal to epsilon by kB is x n kB. We need to find out the value of x. Let's solve this question. Z equal to 2 cos hyperbolic epsilon by kBt whole to the power n. Let's assume that beta equal to 1 over kBt. So this Z can also be written as 2 cos hyperbolic beta epsilon whole to the power n. Now the average energy is given by minus del del beta log Z. This can also be written as minus n del del beta log 2 cos hyperbolic beta epsilon. Taking differentiation with respect to beta, we get 2 epsilon sine hyperbolic beta epsilon by 2 cos hyperbolic beta epsilon. So we found that average energy is equal to minus n epsilon tan hyperbolic beta epsilon. Now the specific heat is given by differentiation of the average energy with respect to temperature. Putting the average energy equal to minus n epsilon tan hyperbolic beta epsilon, we get the specific heat at constant volume is equal to minus n epsilon square sec hyperbolic square beta epsilon into del beta del T. Here beta equal to 1 by kBt. So the differentiation of 1 by kBt with respect to temperature is minus 1 by kBt square. So the specific heat at constant volume is equal to n epsilon square by kBt square into sec hyperbolic square epsilon by kBt. This can also be written as n kb into epsilon by kBt whole square into 1 by cos hyperbolic square epsilon by kBt. Now we need to find out the specific heat at T equal to epsilon by kb. At this temperature we have epsilon by kBt equal to 1. We replace epsilon by kBt by 1 in this expression. Then we get Cv equal to n kb by cos hyperbolic square 1. Cos hyperbolic 1 is equal to e to the power 1 plus e to the power minus 1 by 2. So Cv is equal to n kb into 2 by e to the power 1 plus e to the power minus 1 whole square. After some simplification, we get Cv is equal to 0.419 n kb, but in this question we need to write the correct value of Cv up to 2 decimal places. So this can be written as 0.42 n kb. So in this question we have found that x is equal to 0.42. So the correct answer is 0.42.
Hello, am I audible?
Yes, sir.
Okay. So in this problem, the Z is given. Okay, at temperature T, the n particle canonical partition function is given to you. Okay, this is equal to this thing. Okay, and here we will assume that beta equal to 1 by kBt. Okay. So if you replace 1 by kBt by beta here, then you will get Z equal to 2 cos hyperbolic beta epsilon whole to the power n. Clear? So
Yes, sir.
average energy is defined as this minus del del beta of log Z. Now if you put Z equal to this here, then you will get this. Any confusion here or no?
Sir.
Okay, this is just this thing. I mean, if you have, sorry, I cannot write here. Let's say Z equal to Z1 to the power n. Okay, so log Z is equal to log Z1 to the power n. Now this Z1 to the power n of log of Z1 to the power n is equal to n log Z1. So that's what is written here. Okay, sorry. Okay, now let's differentiate it with respect to beta. If you differentiate log of x with respect to x, then you will get 1 by x. So here we are getting 2 1 by 2 cos hyperbolic beta epsilon. Okay, and now you have to differentiate 2 cos hyperbolic beta epsilon with respect to beta. If you do that, then you will get in the numerator 2 sin hyperbolic beta epsilon and epsilon multiplied by epsilon. Okay, now this is equal to minus n epsilon into tan hyperbolic beta epsilon. Now if you differentiate tan hyperbolic beta epsilon with respect to beta, then you will get I mean this Cv is equal to del del T of energy, average energy So this can also be written as del beta of average energy into del beta del T. Okay. Now if you differentiate the average energy with respect to beta, then you will get minus in epsilon sec hyperbolic square beta epsilon into epsilon, right? And
Sir,
del beta del T is equal to beta is equal to 1 by kVt. So if you differentiate 1 by kVt with respect to temperature, then you will get minus 1 by kBt square. Okay, so here you have minus, and if you differentiate it with respect to temperature, then you will get another minus sign. These two cancel out. You will get n epsilon square by kBt square into sec hyperbolic square epsilon by kVt. Now here we have used that beta is equal to 1 by kVt. Okay, now this can also be written as n kb times epsilon by kVt whole square by cos hyperbolic square epsilon by kVt. Now in this problem, the temperature is equal to epsilon by kVt. It is given already. Okay, so epsilon by kVt is equal to 1 in this problem. It is already given to you. Just put this value epsilon by kVt equal to 1 here, then you will get in kb by cos hyperbolic square 1, right? Now this cos hyperbolic x is equal to e to the power x plus e to the power minus x by 2. So cos hyperbolic 1 is equal to this thing, e to the power 1 plus e to the power minus 1 by 2. Now just use your calculator, then you will get this thing. And in this question, this Cv is given as x into nkb. So x is this thing, 0.42. Okay, clear? Hello?
yes, sir.
Okay. Now I'll show you the derivations of this thing. Average energy equal to minus del beta of log z, and also zn equal to z1 to the power n. Okay, let me share the screen again. Okay. So the single particle let's say this is in particle. Okay, in particle canonical partition function equal to this sum over I e to the power minus beta ei. Okay, now let's calculate this del beta of log z. Then you get this, if you differentiate log z, then you will get 1 by z, and you will also get this del zn del beta. Now zn is equal to this thing. So if you differentiate this, then you will get e to the power minus beta ei into minus ei. Clear? Hello?
Yes, sir. Yeah.
Okay. So what we have get? We have got del beta of log z equal to minus ei to the power minus beta ei by zn. Okay. Now what is the definition of this average energy? This is equal to this. Now let me write it in this way, then it will be very much clear to you. Okay, let's say there are different energy levels with energies ei, okay, and the probabilities are pi. Okay, then the average energy is given by sum over pi into ei. This is clear? Hello?
Yes, sir.
Okay. Now what is pi? Pi is equal to e to the power minus beta ei by z. So average energy is equal to sum over ei into e to the power minus beta ei by zn. So del beta of log z is equal to minus average energy, right? Hello?
Yes, sir.
So average energy is equal to minus del beta of log zn. So this we have derived. Sorry. Now this zn is equal to this is for 3 dimension. Let's generalize it more. Okay. So
The energy term.
sorry, I'm writing. Sorry. So if there are n particles, okay, then the n particle canonical partition function will be given by this, where p1 is the momentum of the first particle, q1 is the coordinate of the first particle, and p2, p3 up to pn are the momentums of the second, third, and so on up to nth particle. Similarly for q. Okay, clear? This is clear. This
So what is
equation
D here?
d is the dimension.
Yeah.
Dimension.
Okay.
So for 3 dimension you write it like this, right? For single particle
Okay.
canonical partition function, let's say this is for single particle, so you write it like this. So d is the dimension, spatial dimension, nothing else. This d. this D is just the volume element.
Density.
Okay, what density? No, not density. This is the volume element. So
It's
for
small volume.
for 3 dimension, this will be equal to 4, no, not 4 pi, equal to this sine theta d theta d phi. Now if you integrate over theta from range 0 to pi, then it will give you 2 and it will give you 2 pi, and the range of phi runs from 0 to 2 pi and theta runs from 0 to pi, and if you integrate the theta and pi coordinates, then you will get 4 pi q square dq. Okay, so I'm not going into these details. Now let's say that this Hamiltonian, let's say the particles are non-interacting. What does this mean? This means, let's say the particle, the Hamiltonian of the first particle is h1, okay, and the Hamiltonian of the second particle is h2. The individual Hamiltonian, I mean, if there is one particle, the first particle, the Hamiltonian is h1, okay, and if you take another particle, then the Hamiltonian is h2, so on up to hn, and there is no interaction between the first particle and second particle. I mean, there's no h12 plus h13 and also h1n or h2n, h3n. Not there are no this type of terms. Okay, clear?
Yeah.
So this is the definition of non-interacting Hamiltonian. So your H can be written as this, sum over I hi. And this hi is function of qi and pi. So for the first particle, so this e to the power minus beta h can be written as e to the power minus beta h1 into e to the power minus beta h2 and so on up to n. This is clear? I have used this just h equal to sum over I hi, nothing else.
Sir, clear.
Okay. Now we'll also assume that this hi depends only on qi and pi. Let's say for the first particle we have the Hamiltonian h1. So h1 depends on q1 and p1. It does not depend on q2, q3, qn up to qn, and also it does not depend on p2, p3 and pn up to pn. Okay, this is clear?
Yes, sir. Yeah.
So in that case we can write this Hamiltonian, this I mean not Hamiltonian, this canonical partition function Zn equal to this h1 q1 p1, sorry, into h2. Here h2 is function of only q2 and p2,
Q2 P2.
right, and so on up to what, the nth particle into e to the power minus hn. So there are many h. So this h is actually, the h in the denominator is Planck's constant, not to be confused with this h1 h2. These are Hamiltonians. Okay, this is actually 2 pi h cross. Okay, now you assume that the functional dependence of this are equal. Let's say this is p1 square by 2m plus some k q1 to the power some alpha. Okay, I am assuming some general Hamiltonian. This is the general form of this Hamiltonian. So this is p square by 2m. This is the kinetic energy plus some potential energy like this. Okay, so in that case we'll also assume that this is equal to this. Now if you use this approximation, not actually approximation, this assumption, then you can write Zn equal to this. To the power n. This is clear, the last step?
Yes, sir. Yeah.
Okay, now what is this inside the bracket? This is the single particle canonical partition function for non-interacting particles. So this is equal to Z1, right?
Yes, sir.
Or is there any confusion?
Sir, is the momentum or position are different, sir?
Sorry?
Currently is
Sorry?
submission or something product. I am saying that momentum and coordinate of h1, h2.
Right, these are all different, but you can do this thing, right? Let's say this is for second particle. So I am assuming this Hamiltonian for your convenience. Okay, I am writing the Hamiltonian here H2. Now these Q and P's are integrated, right? So you can just replace them like this. This is clear? Hello?
Yes, sir.
I am just doing this thing. Let's say you have some function fx, you are integrating it over x. So you can always do just what you are doing here, you are taking x equal to y. There's some noise. Okay. So what is this? This is for the first particle. Similarly, all of these are equal, or is
Yes,
there
sir.
any...
So is it like that they are independent or
Right,
seems like that they are equal to some constant?
Sorry?
I am saying like in method of variable separable, we equate the independent variables. For example, del some function by my del x is equal to del some function by my del y is
No,
equal to some
I
constant.
am not going to that details. I am just saying that let's say you are integrating it. Let's say there is a function fx, and if you integrate it this, now just consider x equal to x equal to y. Okay, then you will get
Yes.
this thing. This is, there is nothing else. I am just doing that.
Okay, sir.
Okay,
Clear.
but this is valid only if the this assumption this approximation or assumption whatever you say holds this
Non-interacting.
non-interacting, and also the Hamiltonian should be similar functional form. I mean h1 as a function of q and p is equal to this, and h2 is as a function of q and p is like this. Okay, this should be similar, otherwise it will not hold. Let's say for one particle you have the, let's say for the first particle there is no potential, the particle is free, then the Hamiltonian will be p square by 2m. And let's say for the second particle there is some harmonic oscillator type potential, half m omega square x square, then it will not work. The form of Hamiltonian should be identical, right? And there is no interaction, of course, otherwise it will not hold. There will be some interaction term. Okay, so
Okay, sir.
Sir, it's for distinguishable particle, na?
right, the particles are distinguishable, but the Hamiltonian should be similar. I mean the functional form of Hamiltonian should be similar. Okay, distinguishable means what? Let's say there are two particles. Okay, what happened? Am I audible?
Yes, sir.
Okay, distinguishable means what? Let's say there are two particles with energy, let's say E1 and E2. This is energy E1, this is energy E2. You place the first particle here and the second particle here. Okay, and if you do the opposite thing, I mean first particle here, let's say this is particle number 1 and this is particle number 2. This dot thing is particle number 1 and this cross is particle number 2. Okay, so here we are placing the first particle with energy E1 and the second particle with energy E2. Here we are doing the opposite thing. So these two are not equivalent configuration, right? If the particles are distinguishable, but if the particles are indistinguishable, then these two are actually equivalent. Clear?
Yes, sir.
Okay. Okay, so if the particles are distinguishable and the particles are non-interacting, then we have this. And if the particles are identical, then we'll have 1 by n factorial. This is called Gibbs factor, maybe, I don't know. So for non-distinguishable particles or identical particles, you have this Zn equal to 1 by n factorial Z1 to the power n. I have explained this 1 by n factorial in previous video, I think, previous class. Okay, if you want me to explain it again, then we can do that in next class also. Not next class, next to next class. Next class we will discuss about Maxwell's velocity distribution and other things, phase equilibrium, so on. Okay. So it's already 7:15. I'll stop here today. We'll continue our discussion on next Saturday from 6 p.m. Okay. Thanks everyone for joining. Thanks.
Thank you, sir.
Thank you, sir.
Thank you, sir.